So let's get started slowly as the audience will join. We are very pleased today to welcome you to this session of the networking channel. With Jim, we are just going to set up the scene. Jim, in your book now you have a new chapter on mobile and wireless, as well as you teach a class on mobile and wireless. So I guess this topic is of utmost importance for you and for your students, which is related to the evolution of the cellular networks, right?
And you teach a class on it too, Serge.
Precisely. So today we are very lucky. We are very pleased that KK Ramakrishnan set up this wonderful panel. So KK is a professor at the University of California, Riverside, but again, everyone knows KK. For me, it's like I know you since ever. I remember reading this wonderful paper related to the deckbit congestion avoidance back, I think, in 1988, published at SIGCOMM, and that received the SIGCOMM Test of Time Award paper in 2006. And KK also joined the AT&T Bell Labs in '94, and he was with AT&T Lab Research since 1996, and now with University of California at Riverside. So he has done an amazing work. I'm not going to mention all, but amazing contributions related to the domains of congestion control, multicast communication, SDN, and so on and so forth. But today, we are very pleased that KK put a wonderful panel, which is going to talk about cellular network, will reality meet the promise? Just before we start, I would like to remind the audience that we have a Slack channel where you can continue the conversation once the session has ended. That, of course, the session is recorded as any other session, and that you can find all the information about the networking channel on the web page. And you are most welcome to start asking questions, preferably using the Q&A, as ever you feel comfortable with it. So without further ado, KK, thanks again, and thanks to all the panelists. The floor is yours.
Thank you, Serge. Let me share my screen with some introductory slides. So as Serge said, we're going to be trying to talk about whether the evolving cellular networks can support all the emerging new applications. The main reason we thought it would be interesting to talk about this is because there are so many mobile applications that are coming up now that need high bandwidth, low latency, and ubiquity in terms of communication. And cellular networks have been promising to do that, whether it is the 5G that is being deployed these days and what we expect to see in the future. And they are leveraging higher bandwidth wireless channels, and it does improve one component of the end-to-end path with new radio technology. But there is a price that we pay with that higher bandwidth. It comes with reduced coverage often. But more than anything, latency is still a challenge. And as Dipankar will speak, it's an end-to-end problem that needs a holistic architectural solution. And so we thought that it would be good if we can have a discussion about what are the ongoing efforts to meet this challenge, both in research and in industry. So there are four of us who are going to be having this discussion. First is Professor Dipankar Raychaudhuri from WinLab, Rutgers, David Allabaugh from Fujitsu Network Communications, Dimitrios Koutsonikolas from Northeastern, and myself, KK Ramakrishnan from UC Riverside. Let me actually introduce each of them so that we can then easily hand off to each other for a little introductory presentation from each of us. Professor Raychaudhuri, we all call him Ray, is a distinguished professor in the Electrical and Computer Engineering Department at WinLab, which is at Rutgers University. And he was the director of WinLab for a very long time, as long as I can remember, from 2001 to 2024, and did a number of wonderful things in WinLab. I've known him from before as well, and he's been working on wireless for all the time, and he's been responsible for having a really good industry university research center on specializing in wireless technology at WinLab. The things that it's known for is the Orbit wireless testbed that so many of us use. He was also responsible for the Mobility First Future Internet Architecture project, and now leads the Cosmos project under the NSF Power program. He has spent time before in industry, starting with being the head of broadband communications at Saranov. Then he was at NEC Lab as assistant GM and department head. And then he was also a chief scientist at IOSpan Wireless startup. He got his BTech from IIT Kharagpur, and then MS and PhD at Stony Brook. He's an IEEE fellow. He's received so many awards, not only at Rutgers, but also from IEEE, the Donald J. Fink Award. He is a distinguished alumni from IIT Kharagpur and the Schwarzkopf Prize for Technical Innovation. Welcome, Ray. The next is David Allabaugh. He is a software solutions architect and strategic planner at Fujitsu Network Communications. Has a lot of years of experience, and he's responsible for new architecture designs, proof of concept validation, and implementation of network software offerings, especially related to 5G service management and orchestration. He and I worked together on a project where he's really been very knowledgeable about the work that goes on in ORAN. He's participated in organizations for Open RAN, MEF, and TMF consortia. And he is in Fujitsu, which is a provider of digital transformation solutions for network operators and service providers. And they're doing a lot in the cellular network space. He was at Tel Labs before and also at Corient. Welcome, Dave. The third person is Professor Dimitrios Koutsonikolas. He is an associate professor in the Electrical and Computer Engineering Department at Northeastern and a member of the Institute for Wireless Internet of Things there. He was an associate professor at the Computer Science and Engineering Department at the University of Buffalo in SUNY, and he has been doing a lot of work on experimental wireless networking and mobile computing. His current focus is on 5G measurements, which he'll talk about, and also in terms of network protocol design and application design. He got his PhD from Purdue University in 2010, and he's received a bunch of awards, including the NSF Career Award, the IEEE Region 1 Technical Innovation Award, and a whole bunch of Best Paper Awards, and a number of teaching awards from the University of Buffalo. So what I will do at this point is invite Dipankar to make his pitch about this topic, and then we can go to David and Dimitrios. Dipankar?
Yeah, I'm sharing the slides. Can you
Yes,
Do
you
you
need to
see
put
it?
it in slideshow. Yes.
Yeah. Okay, so thank you, KK, for the introductions. And basically, KK asked me to give a brief introduction, so I'll continue on that. I won't be presenting results from the individual research areas, but we are also working on each of these. And hopefully during the discussion, we can talk more about networking or edge cloud aspects that we are working on. So just to start the discussion, I think for this group, it is quite well known that there are a number of emerging applications which could be enabled by a new network, which will offer ultra-high bandwidth, low latency, and powerful edge computing all within the same framework. And that will then enable different application domains, which are part of the focus of our discussion today, which include augmented reality, virtual reality, connected car, smart city, and industrial control, and so on. So there are a number of both public-facing as well as private applications that could potentially change significantly the economics and quality of these applications. The autonomous driving is an example. There have been a lot of partial failures of autonomous driving because many of them were completely local and relied entirely on image captured by the car in a distributed way, which has some good properties, but you can also think about how edge cloud can add to that by providing a more global view. So these different pictures that I have here are just different examples of what you could try to achieve with a next-gen network. I will refrain from using the term 5G or 6G because these are kind of arbitrary. But I think broadly we recognize that mature LTE products will enable a certain set of applications. If you need a lot more bandwidth, or if you need to integrate some aspects of edge computing, you have to wait for the 5G solutions. And some of those early solutions do not fully integrate edge computing. And then there's also limitations on latency, which we will encounter in all of these applications. So latency is something that has become sort of a buzzword, and there are a lot of attempts to define what latency is appropriate. So many of the early specs of 5G expect that number to be less than 10 milliseconds, which is quite challenging with many of the systems that we are talking about here. But we can discuss a bit further and see where that takes us. And then when you have industrial control as a private application, there too you can think in terms of optimizing the system to a level that the latency, achievable latency is below 10 milliseconds, potentially approaching 1 millisecond for some of the more challenging applications, although there are not too many that require that lower value. So I'll just mention a couple of scenarios. One of the scenarios that we're looking at is sort of a decentralized edge cloud scenario that goes along with the access from the mobile devices. And this is very much a new type of application that can only be served if you had strong edge computing close to the device. And that in turn has to go through a network, which you can see here that there are these blue clouds are the mobile core networks, or MEC, the mobile edge cloud network. So we can have multiple MECs which are spawned by different users. This is not a coordinated deployment. So the idea is that in a smart city scenario, you may have multiple providers who decide to pool their resources in a federated manner. And that leads to some interesting details to be worked out about how the edge compute will work for clusters which are decentralized and potentially owned by completely different entities. So this architecture is broadly what we are looking at. And then you have the problem that many of these applications are very compute hungry. And so the mobile device cannot do everything, and you have to ship the data or part of the data into the edge cluster. So this is a type of application which we think is more or less representative of what we need to do, both in terms of bit rate and latency. And this could become a large-scale use of this type of service would, of course, require a good scalability model as well. So we can discuss further as a group, and I'm sure you'll hear some solutions coming from the different talks. And this is just another diagram. I think I'm going to skip over this, but essentially it shows a more focused smart roadway example in which autonomous driving benefits from a more centralized view of what is available and what is going on the roadway, and thereby can provide some kind of situational awareness, which is much better than available today. So we want to talk a bit more about latency in this panel, and the idea of achieving high low values of end-to-end latency is an important one for 5G as well as 6G as a whole. So we can see in the simple diagram shows you how it breaks down. You have the radio and 5 MAC latency, which is usually relatively small, and the targets are 2 millisecond or lower. And then you have a mobile core network, which adds a significant amount of latency the way it is designed today. And then beyond that, you have the cloud service latency, which we will talk more about in different parts of this discussion. So just to give a benchmark number, so there you can see that existing latency measurements from commercial systems are very large latency, and many of them are approaching hundreds of milliseconds. As you can see, I won't go into the details of these plots, but you can see there's a distinction between data plane and control latency. So the control plane being, for example, you have over 250 millisecond latency in some of the plots that we have here. So that's just the background that there is a lot of challenge to reduce some of these latencies, typically by more than 1 order of magnitude. And this is my last slide. I just want to mention here that latency, as KK just mentioned, is really not something that follows Moore's law, but is more about architecture. So we have to think about how to carefully reconsider all the different protocol layers and replace some of them which become too heavy or inefficient. And so there are opportunities in each of these 3 areas for latency improvement. Physical 5 MAC, which has progressed quite well, is the redesign of coding, MAC frames, and error control. And all of these are described in a number of papers already for 5G. Then mobile core network part, we really need to revisit the network architecture, and that's something my group has been working on for the last 5 or 6 years, where we try to come up with more of a clean slate solution, which can result in significantly improved latencies and end-to-end application latency using concepts from information-centric networking, again, something that KK has done a lot of work on. And we also have our own identifier-based routing called Mobility First, and using that, we're able to realize much simpler and much lower latency protocol stacks for the mobile edge cloud, the mobile core network. And then finally, for the third set of issues is that you have to think now not only about building a network, but edge cloud enhanced mobile core network. And there's some linkage between these two, because you need to be able to route efficiently across this network and not have to do things like current things, which include creating tunnels and gateways. So the tunneling and gateway approach is okay up to a certain point, but when we talk about really low latency, you want the routing to be direct, and you want multiple ingress and egress paths, and you want to be able to place network functions along the route. So a lot of people are now working on aspects of this, and I just mentioned a few of the solutions, which include federation, virtual network function placement, application-aware routing, real-time scheduling real-time scheduling for the edge cloud performance, which traditionally has been very centralized. How can you make this more distributed and lower latency? End-to-end TCP performance is a serious problem that still hasn't been solved. Dynamic container migration. So this is just a laundry list I gave for a few topics that we could discuss today. But I'll stop here and pass it back to KK, and we can go to questions later. Thank you.
Thank you very much, Ray. Thank you very much. There's a lot of work going on in the radio access network and in the ORAN context, and I'll have David speak to that. Can you stop sharing, Dipankar?
Yeah, I'm just doing that.
David?
Yes, I'm trying to get sharing working. Okay.
Okay.
All right.
We're in display mode and should be ready.
Let me try that again. It is not switching. Yeah, unfortunately, it wasn't switching on me. So let me try that again. All right. So let's talk quickly about some of the ways that operators and the vendors are trying to meet some of the 5G and modern network application needs. And one of the ways that we're doing that is using ORAN. So I'm going to talk today about some of my observations as to how some of these application challenges can be met using ORAN in particular. There's a lot of ways to do that, but ORAN has some key things, so we wanted to bring that to light today, right? So what are some of those needs? We've already gotten a couple of examples specifically from Ray. In general, some of those are low latency, dynamic network applications, things that change over time, sometimes rapidly, sometimes less rapidly, and high reliability, right? Those are just examples, and the use cases will vary and evolve over time. We have to be ready to respond to all of those, and oftentimes deploy multiple of those simultaneously on a common network. So that's a big challenge. So I wanted to talk to you a little bit about ORAN. So I'll give you a crash course on some of what ORAN's about. So ORAN Alliance is comprised of operators, vendors, research and academic institutions, government agencies, a broad swath of the involved parties, right? It's created with a mission to reshape the RAN industry to be more intelligent, open, virtualized, and fully interoperable, right? So it's building on existing standards in a lot of areas, whether they're 3GPP for network and mobile applications, it could be Etsy or Kubernetes for cloud-based technologies, a lot of transport things. All of those aspects come in, and ORAN aims to build on top of that, extend and enhance those things. It does things like creating specifications, coordinating testing and integration. It collaborates with and supports open software development. It coordinates demonstrations of technology, whether it's open source, academic concepts, or commercial products. All of those are in play for ORAN. So there's a lot of activity going on, and everyone could look at taking part in that. So a little more specifically, what is ORAN doing? So they're looking to enhance and further open the architecture and interfaces for RAN functions. So what do we mean by RAN functions? We're talking about what traditionally was a BBU. Now it's decomposed into central units, both control and user plane, distributed units, radio units, and the software and environment that supports that. So that is what we're talking about. The thing that talks to the UE, the cell phone or other device at the edge, that radio, all the way back to where you hand off to a core network that handles all of those applications. That's the access network, the radio access network. So beyond the traditional RAN functions, the enhancement of those, we're specifying cloud platforms for RAN virtualization, pushing virtualization, moving to containerized cloud native, and specifying not only the architecture for that, the packaging for that, the lifecycle control for that, but also the cloud environment and how the operational systems interact with that is a big part of O-RAN. Enhancing the traditional EMS, NMS operation system concepts is a big part of that. And the term service management and orchestration, SMO, has come out of O-RAN, and O-RAN is the leading definer of those concepts, and has been binding that together and enhancing all the different pieces and the overall concept of that, and moving towards standardized environments so that we can have enhanced versions of that. And then finally, a big part of this is enabling enhancement of analysis and optimization approaches. So traditionally, this has been something that we call SON. Now it's been progressed into concepts that we'll refer to as RAN Intelligent Control, or RIC, right? So there's both a non-real-time RIC and a near real-time RIC involved for slightly different aspects and applications, and we'll talk a little bit more about that. So when we look at all those aspects, what are some of the key pieces that we should be looking at to help meet those application needs? So first, there's an examination of those overall use cases. And O-RAN has done a lot of studies and uses those studies to decompose into use cases and drive into the requirements into the specific components. So whether it's V2X, vehicle to anything, UAVs, IoT applications, energy savings within the RAN, spectrum sharing and interference mitigation, and just general RAN performance and quality enhancements. Those are things that O-RAN is looking at. And you could look at the use cases to understand how they're approaching those and potentially become involved or add suggestions to that. RAN virtualization. I talked about moving from traditional appliance or physical-based network functions into cloud native, right? The softwarization of the RAN is a big push, and O-RAN is part of that and is moving beyond just the functions, but looking at the environment, the cloud infrastructure, how you interact with that, how you package your functions, deploy them, lifecycle manage them. Those are big pieces as well. Service management and orchestration. How do you pull the pieces together and define your services that meet your application needs, and then deploy those and coordinate those in multiple applications in the same network? That's all done using the SMO. It enhances your traditional EMS, NMS, OSS, which were highly manual, and provides automation so that you can handle those dynamic use cases and optimize for each of them and balance between them. And then finally, the RIC, the RAN Intelligent Control. It is striving to provide an open way to do analysis and optimization. So it allows standard APIs to be used to have apps that can come from a variety of sources and use relatively standardized models and those interfaces for those apps to be able to get information and for you to deploy into these environments and not be vendor specific, but apply across multiple network needs. So that gives us a broader set of people and technologies that can come in and start to apply and optimize and analyze these networks and help us meet these needs, right? So the near real-time RIC is deployed out at the edge, and it handles that optimization on ranges from like 10 milliseconds up to a second. And then the non-real-time RIC is a centralized process that coordinates across broader sets of the network and handles cases above 1 second. So all of these can be applied to meet some of these application needs. So now, what is some of the structure inside of O-RAN to meet those activities? There's a lot of different working groups within O-RAN. There's also focus and research groups. There's the software, especially the open source coordination. There's plug fests where we do the demonstrations. So as we look at some of those pieces, if you want to look at use cases, you'll go and you'll look at working group 1. They have specific documents and meetings to discuss use cases, and you can take a look at that. If you want to look at virtualization, you'll focus largely on working group 6. Working group 6 is the cloudification and orchestration working group, where they define, like I said, the packaging, the lifecycle management, and the environment that the RAN is cloudified and deployed into. The SMO is crossing a lot of different groups. It flows largely out of working group 1 with the overall architecture, but has aspects in things like non-real-time RIC, the virtualization aspects, the OAM aspects, so a lot of different things pulled together and apply into the SMO. The RICs themselves are handled in working groups 2 for the non-real-time RIC and working group 3 for the near real-time RIC, depending on which kind of application you're most interested in. The software, you can participate in OSFG, the open source focus group, and also the ORAN software community. So that's an open source Linux Foundation based project where we take a lot of components based on ONAP and advance those to meet a lot of the open source needs and do proof of concept on this. And then demonstrations largely centered around plugfests, but there are other activities as well. So quickly, I want to talk about Fujitsu bringing these pieces together. Fujitsu has offerings that address all of the ORAN components. They're modular, can be deployed independently, but we have a coherent solution for this. Includes the radio units, fully virtualized CUDUs, a SMO, a near real-time RIC as well that's deployed out at the edge, and then applications that deploy on top of that to do things like energy efficiency, handover optimization, load balancing, slice optimization and monitoring, and a wide variety of different applications there. So there are commercial deployed solutions that are out there and available in the real world. And ORAN is a good way to provide us an open environment to operate in. And at Fujitsu, we're supporting that multi-vendor ORAN environment and exploring ways to address these use case needs and the challenges that we have throughout the entire network. All right. So that's a quick overview of how we can take some of these challenges and potentially use ORAN and some of the efforts there to study and address some of the challenges. Thank you.
Thank you, David. Let's come back to looking at latency. Dimitri, can you speak?
Yes. Okay, so I'm going to briefly talk actually about my group's efforts over the past 4 years to measure 5G performance or more broadly cellular performance in the wild, and a few high-level lessons out of these measurement campaigns. So I guess Deepak already talked about that, right? We are about in 5G's midlife now, right? 5 to 6 years since the initial rollout. We have seen rapid deployments by major cellular operators. We have heard of the promises, and actually those peak data rates that I'm listing here are a reality. Recently, we measured 1+ gigabps with mid-band 5G, even on the highway. With millimeter wave, you get up to 4 gigabps. And all those, this high bandwidth, the low latency that 5G promises have the potential to unlock all these new applications that we often call 5G killer apps, like panoramic or volumetric video streaming, VR, AR, cloud gaming, connected autonomous vehicle applications where vehicles upload LiDAR or camera data to a cloud or edge server, right, for collaborative perception, and so on. And all those applications created, well, we all know that, a lot of hype even before the initial rollout. But the question is, 6 years after the initial rollout, are we there yet? I guess that's why we're having this panel today, right? So how close are we to fulfilling, for 5G to fulfill its promise? So there are many challenges, and again, Dipankar kind of went over some of these challenges, right? First, you have uplink downlink asymmetry. 5G, similar to its predecessors, it's a highly asymmetric technology. The uplink bandwidth is an order of magnitude lower than the downlink bandwidth, but many of these 5G killer apps are actually uplink oriented. Then, as you go to higher frequencies, you get shorter range, and in the case of millimeter wave, you get also blockage. And the shorter range means additional problems during mobility, right? More handovers, more disruptions, and in the case of millimeter wave, also more beam misalignments, more overhead to realign the beams. And overall, I would say 5G is a very complex ecosystem compared to its predecessor technologies. You have the UEs, the RAN, the core that KK will talk about, the protocols. Then as you move to virtualized disaggregated architectures, the edge and cloud servers start playing a big role. And then you have all those new applications, which we don't know how to design them, right? Because we didn't have 5G until now. So those applications are also edge or cloud assisted. So again, the cloud plays a big role. The application architecture itself plays a big role. Then you have diverse frequency bands. You have diverse architectures. As I mentioned, we are in 5G's midlife, and still we don't have a full 5G standalone coverage. And we have diverse operator policies. And all these call for large-scale measurement studies to understand the potential and limitations of 5G deployments and improve future deployments. My argument is you cannot improve something unless you measure it and see how it really performs in practice. So this is what my group has been doing for the past 4 years. We've been driving across the country and measuring performance. And here's a summary of the measurement campaigns we have done. I will focus today on a few high-level results from 2 real cross-country measurement campaigns from Los Angeles to Boston, done 2 years apart in 22 and 24. And this is the setup that we use for this campaign. So we have 3 phones, each connected to one of the major operators, measuring performance in parallel. And then each phone connects to an XCAL device. This device taps to the Qualcomm diagnostics interface and logs all the signaling messages exchanged between the base station and the phone. So then we can do a lot of analysis using extracting lower layer KPIs, signaling, and so on. And we deploy a bunch of Amazon servers across the country for each of these campaigns. We have cloud servers, and then in the case of Verizon, we also use wavelength edge servers. These are servers attached to the Verizon core network in select cities for edge computing. So let's take a look at the evolution of coverage, network performance, and application performance in 2 years based on these 2 measurement campaigns. So this shows the comparison in terms of coverage. And ideally, you are looking for yellow, orange, or red. This is 5G, right? Or even better for orange and red. This is the true high-speed 5G, mid-band or millimeter wave. So back in 22, that was already 3 years after the initial rollout. Coverage was kind of disappointing, right? There was one operator with satisfactory coverage, 70%, but out of that, only 40% was mid-band. The other 2 operators, the amount of 5G we experienced driving from Los Angeles to Boston was about 20%. In 2024, in 2 years, you see a big improvement, right? One operator, T-Mobile, reached now 90%, with most of it actually mid-band. The other 2 operators more than doubled their coverage, right? But we're still far from satisfactory. Now this slide compares the performance in the terms of CDFs, again in 22 and 24. And again, we see a big improvement in throughput within 2 years. Back in 22, you can see a median downlink throughput of 10 to maybe 30 megabps, really very far from what 5G promises. Of course, a lot of this was LTE, right? In 24, you see mid-band, you see downlink performance going from 70 to more than 300 Mbps. Even better in uplink. Back in 22, you were getting just a couple of tens of megabps in the median case. Now you are getting 20 to 40 Mbps, so that's 2 to 4x improvement. What has not really improved in 2 years is the latency, the round trip time. With the exception of one operator, AT&T, the other 2 operators are either at the same level or actually slightly worse. And remember, many of these applications that we've been talking about, these new applications, they are not only bandwidth sensitive, they are also latency sensitive. Dipankar talked about CAV applications here. Many people cite 100 millisecond end-to-end latency from the moment you capture a LiDAR frame to the moment you get the inference result back from the server to avoid, for example, accidents, crashes. We see that this is not always satisfied in today's 5G. The other application that Dipankar mentioned, augmented reality, offloading 30 frames per second to an edge server to do object detection and get the result back. You need an end-to-end latency of 33 milliseconds. You can barely achieve it with today's deployments. And then for VR, you need a motion to photon latency, typically less than 15 milliseconds to avoid dizziness. That's very far from reality. A good thing, we noticed a lot of operator diversity in both our trips, right? So this slide showed the CDFs of the throughput difference between every pair of operator at the same location and time. And you see that there is no operator that performs consistently well consistently better than the other two across the country, right? So that suggests that perhaps multi-connectivity solutions like MPTCP, MPQuick over multi-SIM phones can improve both performance and maybe latency. This is not a common thing in the US, right? Multi-SIM phones. It is common in other countries, so maybe we should start looking into this. And I will finish with one example of how an application performs in those driving scenarios. Here we have this augmented reality application that performs 30 frames per second to an edge server. The server performs inference and sends the result back. And we plot the end-to-end latency, the number of frames per second that we offload, and the accuracy expressed in this mean average precision. This metric goes from 0 to 100%, the higher the better. So the black lines here show the best static performance we measured across this trip with edge server and millimeter wave facing the base station. And then the red lines are CDFs of the driving performance with and without compression. So we see that AR performance is severely impacted by driving. Compression certainly helps a lot, but still not enough. In fact, what you also see is that even the best static performance is very far from optimal, right? You are targeting 30 frames per second, and the best you can offload is 13 frames per second under the best static conditions. And here we try to see the impact of high-speed 5G and edge computing. So the x-axis shows the percentage of time that during a given run when we were using mid-band or millimeter wave. And then the red bullets are runs with cloud servers, the crosses are runs with edge servers. So we see that the combination of high-speed 5G and edge improves the worst case performance. You no longer see any points down here, right? When you have 90 to 100% 5G and edge computing. But still, the best case performance is, as I mentioned before, very far from the desired performance, right? You get a best case accuracy of 40%. We found similar results for 3 other applications, both uplink-oriented and downlink-oriented, which I will not describe here, but I'm happy to discuss. So to summarize, 5G offers hundreds of megabps up to several gigabps of data rates, but only in ideal scenarios and only in the downlink direction. Coverage and performance have improved dramatically over the past 2 years, but they are still far from perfect. And today's network still cannot support that next generation of 5G killer applications. So takeaways from these studies, high bandwidth alone is not enough. Many of these applications are also latency critical. So end-to-end latency matters. And to reduce the end-to-end latency, as was also mentioned by the previous 2 speakers, right? Edge computing is important. It's not enough to innovate at the run and bring the run latency below 1 millisecond. You have to reduce the end-to-end latency. And another important aspect here is software level optimizations at the application level, even simple ones like compression and local tracking still matter. We have examples actually where we change the architecture of an application and we can change completely the performance. We can mask the latency, for example, under the exact same network conditions. So my final conclusion here, I guess, is that hardware advancements on both the UE and server side, but also innovations across the full networking stack are needed to support the next generation of mobile applications. I'll stop here, and all our data sets from all the measurement campaigns are available on our website, and we hope people will actually use them and will find them useful. Thanks.
Thank you, Dimitrios. I'll try to cover a little bit of what we've been doing as quickly as possible, maybe in 5 minutes. So we've been working on building a cellular core network with a number of people, including people from NYCU in Taiwan. The main reason that we've been working on a core network is because it is providing the central control and management for mobility, for user session management, and all the other aspects, so that it becomes really the gateway to go into the internet or the cloud. And so when we look at the cellular core, it plays a very important role in terms of both data forwarding as well as handling the control plane that is so important in a cellular network. Because there is a tight dependence between the control and data planes. Before a mobile device, a UE, can exchange data packets, you've got a whole bunch of control messages that have to be processed by the central core to set up the data path. And each action by the mobile device involves many message exchanges between the functions in the packet core and the radio access network and the UE. And all of that, as we move towards this virtualized environment and adopting a REST interface for interactions between these different network functions, we end up having a fairly significant amount of additional penalty that we pay for all of these control plane functions that interact with each other and with the user plane. So one of the things that is been popular for a long period for us is the separation between the control and data plane. And in the context of a cellular environment, that is particularly painful because we've got such a tight coupling between the control and data plane for setting up connectivity, for all the other interactions that occur. And when we started, we said, why not change the control plane protocol entirely? And that was much more of a challenge to be able to change because that required the whole ecosystem, the world to change. And that will eventually happen, I believe. But in the meantime, we said, let's look at how to improve the implementation to help in lowering this latency, especially for the control plane. And whether it was in terms of system implementation, in terms of simpler protocol design modifications, as well as from better handling of the control plane activities. So one of the things that we see with using this 3GPP standards recommended approach is that there is a lot of interaction between the network functions, all of them going over this thing called the service bus interface, which uses a kernel-based HTTP REST API, and that contributes a lot to the control plane latency. When we look at the protocol, for every exchange, whether it is for handover, for a simple paging action, which is to have a end user device move from idle to active because it is looking to conserve power, there's a large number of message exchanges. And if you look at it in terms of all of the components that are involved in the core and the radio access network, you have such a large number of protocol exchanges. And it's nice to see the color here. It looks colorful, but that's the number of different components that are involved in that interaction. And another thing that we see as we go to higher speed radio channels is smaller coverage area, and you have much smaller cells, so a lot more handovers, and that means there is a lot more work that has to be done over the slow core network. And so we said, let's look at how we can overcome a lot of the implementation penalties that we typically see with this kernel-based networking protocol stack that we use in the core network, which involves data copies, protocol processing, and all of that we've been complaining about in many contexts. And we ended up saying we can actually do something about it by adopting a framework that we've been working with, which is to look at using shared memory as much as we can and to reduce the dependence on the kernel protocol stack as much as possible. And so we built a core network implementation built off of a fully 3GPP compliant free 5GC core implementation, and then built on top of that the shared memory framework, and to then make sure that we can have the right interfaces for both asynchronous and synchronous operation, and to be able to support a large number of connections. So we've created this open source framework, and we see that by having the same, more or less the same protocol implementation, we can improve the latency in terms of session establishment by a factor of 2. We've also put this on the Fabric testbed and are able to get the tasks like a idle to active transition improvement by 30 to 40%. And overall, this core network has helped us to ease some of that stress on the latency contributed by the core. We've implemented this with the most current release 17 version of the core network and it's almost ready for us to release it. And we've also planned to put it out on the Fabric testbed for the community to use. And one of the things that we are imminently going to have is the ability to support dual connectivity. And once we have that capability, then we will also be able to ease some of the penalties that come from handovers by being able to smoothly use multipath to be able to move from one base station to another with more or less seamless handover. So we think that there is potential, but we would like really to be able to go further and simplify the protocol, but hopefully that'll come in the future. So let me open up the floor for some questions that we can all answer. Jim had one question on the chat, which was to say, well, how can the community experiment on this with whether is it with the Power Platform? What about people outside the US? What can they do? Ray, would you like to pick up on that and talk about how maybe Cosmos can help?
Yeah. So can you hear me?
Yes, please.
Yeah. So definitely that was one of the focus areas for the Power Platforms when they got started a few years ago, about 5 years ago. And in our particular testbed called Cosmos, there is a focus on integrating high-performance computing with a very fast optical backend with the front end, which is a fully programmable SDR fabric. So there is the tools are there. The challenge now is, having enough expertise to run such a experiment and make latency measurements. I've had some students working on aspects that we were discussing just now, where we try to make measurements for different kinds of edge compute and mobile core network functions. So it's possible to use Cosmos for that. And as I said, that I think the whole setup is geared towards latency. So each of these testbeds had different focus themes. And in our particular case, we also have some application-ready environment where you may see some publications we have related to smart city, smart intersection in particular. So there are some data being streamed from multiple cameras and radar devices in the 120th Street and Amsterdam intersection. And so you can use that as well as a starting point so that you don't have to do all the work of building the mobility app. So I realize, of course, that a mobility application being tested in a thorough way requires a lot of manpower and logistics issues that come up. But again, if somebody is interested in it, there's no doubt that it can be done. These are different testbeds from some of the earlier networking testbeds that we had before.
And on our side for our core network, I know I hurried through my presentation, but our core, we're going to put it on Fabric so that people can experiment with it openly as well. Dimitri, maybe Northeastern has some facilities as well with Colosseum that people can use.
Northeastern, first of all, manages the power platforms, right? So, although I'm not part of that effort, Colosseum is the alternative as an emulator, right? Colosseum is the biggest emulator. You can still run end-to-end experiments. Of course, the signal will not go through wireless, right? It goes through wires and it is emulated. But yeah, that's another option, perhaps even before deploying something to one of the power platforms. And then the other option is, of course, to use data sets, and that's what we hope to do, right? To use realistic data sets, at least to do realistic simulations or emulations. We also have smaller test beds here, but yeah, currently for end-to-end, I think the power platforms are the biggest option, the best option, right? Potentially first running your results on Colosseum, testing them, and then moving to a power platform.
Mary, you had a question. Let me see if I can answer quickly, and then maybe David can as well.
I think
we
David
agree.
is answering that, KK.
He's not yet, the answer is being typed, but let me speak briefly to it, which is that yes, there are a number of things that we can simplify. One of the things that we've been looking to do is to eliminate this tunnel setup and to be able to use more of an core IP-based framework for being able to have communication, as well as to see if we can use approaches like MP-Quick for being able to simplify some of the protocol exchanges that happen. David, you were going to talk about ORAN. You were beginning to type.
Yeah.
Go ahead.
So I'll try to quickly hit a couple points. So I think the internet comparison is interesting, but maybe not completely accurate. Wireless networks themselves are inherently complex. What ORAN has done is opened that, and by trying to open it and further standardize interfaces, architectures, and approaches, that's the first step in making that more accessible for people. There's not really a plan to make that, to try to transform wireless into a consumer-facing thing. This is inherently something for network operators. So it's not really an internet transformation that we're looking at there, but making it more accessible to network operators is the goal, and openness is key for that.
So I think we are close to time. What I'd like to say is that we would, all four of us would be very happy to answer questions on Slack over time. And you can also reach out to us and we'll be happy to answer questions as well. Jim, it looks like we are up on time. There is one more question, but I think we'll look to answer that on Slack.
What we're going to do is we'll copy the webinar chat and the Q&A over to Slack, and it'd be just wonderful if all of you would participate in that. And maybe we could sort of continue on the discussion of the question that Marie-José asked as well about cellular sort of not taking the internet turn, because I think we're just sort of scratching the surface of it. Well, on behalf of everybody, you folks, thank you very much for a really, really scintillating and interesting panel. It's really wonderful. And KK, thank you in particular for organizing people and getting the panel together. So thanks.
Thank you all very much.
We want to just do one thing. We want to just promote every 2 weeks at this time. We have during the spring and fall semesters, we have a networking channel event, and the next one is being organized by Marco Marsan, and it's on underwater communications and networks. And you can see I guess, Serge, you're showing your slide, right?
Yes.
Okay, great. So we can see
The panelists.
the upcoming event on underwater communications in 2 weeks. And I think
Excellent.
that it's 12 noon. We always promise to stop on time because people have other things they've got to do. So thank you all again for a really a great event.
Thank
Thank
you
you.
for the opportunity.
We'll see you on Slack.
Thank you.
Bye-bye.
Thank you. Thank you
Thank
all.
you.
Thanks a lot.
Thank you. Bye.
Bye.
Bye.